So here we're looking to differentiate the natural log of x, ln of x. And remember, another way to write that is just log to the base e of x. So if I define a function, f of x, to be this natural log of x, or my log to the base e of x, then by the limit law theorem for derivatives, my derivative function, my gradient function, f prime of x, would be equal to the limit as h tends towards 0 of f of x plus h subtract f of x divided by h. Now if I start to substitute some values in here, now instead of writing the limit as h tends towards 0 each time, I'm just going to put a couple of dashes to show that that's continuing down the page. Now f of x plus h, well, I take my function of x, and everywhere I see an x, I'm going to put an x plus h. So I get log to the base e of x plus h. Subtract my function f of x, so just log to the base e of x, all divided by h. So this is just equal to, again, the limit as h tends towards 0, of 1 over h. Okay, now what I've got left is my log to the base e of x plus h minus my log to the base e of x. So I've got that numerator. Now I can use my log laws to simplify that numerator to become log to the base e of x plus h over x. So we've got a subtraction here in our numerator. Okay, so we can use the subtractive law or the difference law for logarithms, and we take our x plus h and we divide it by x. Now, instead of writing 1 over h, we're going to do a little trick here, and I'm going to write 1 over x times x over h. Okay, so you can see there that that fraction would still simplify down to 1 over h. Okay, again, multiplied by log to the base e, and instead of x plus h divided by x here, I'm going to split this up into two fractions. So I've got x over x, which is just 1, and I've got my h over x, which is what's left over. Now, I can simplify this down a little bit more. Again, the limit as h tends towards 0. Now, if I take my 1 over x, so keep this part here, but this bit here, I can use the power rule of logarithms and go and pop that up to the power up here. Okay, so that's the power rule of logarithms. I get 1 on x times log to the base e of 1 plus h over x all to the power of x over h. So you can kind of see, based off of this bit here, I could rewrite that as I have done in the line above by bringing this power out the front. Okay, so that's just the power rule of logarithms. So what do we have? Well, my limit as h tends towards 0 is going to have no dependency on 1 on x. So I can just bring that straight out the front. So it's 1 on x times the limit as h tends towards 0 of this guy, what's left over. So log to the base e, or my natural log of 1 plus h on x to the power of x over h. So now if we examine what's going on in here, okay, as h tends towards 0, we'll be able to see what the overall limit is going to be. So what we've got here is a couple of graphs, and I've taken this bit in here because this is what we're looking to see what happens as h tends towards 0. Okay, so we want to see the behavior of this function as h tends towards 0. And I've plotted those in these equations down the left-hand side here. So you can kind of see that this bit here is when h is 1. This one here is when h is 0.5. This one's when h is 0.2. All the way down at 0.1, at 0.01, and at 0.0001. Okay, and we're going to look at the behavior of what happens for any given value of x as h tends towards 0 down this set of equations. So if we start off when h is 1, so here, we can see that there's no real consistency. If I take a value of x to be here, for example, that's very different to the value of x I get when I take this value of x, so I'd end up with a larger output over here. But what we can see as we come down this left-hand side and h gets closer to 0, so here h being 0.5, all the way up to when h is 0.0001, we see that at no matter what value of x I take, I'm getting a consistent output. We're getting a horizontal line here. And that consistent output actually turns out to be at about 2.72-ish, okay, which is actually the value for E. So this entire part in here, as h tends towards 0, this bit inside is tending towards E. So we can rewrite this limit as 1 on x times log to the base e of e. That's the behavior of this bit inside as h is tending towards 0. And the natural log of e, well, what do I need to put e to the power of to get e? Is just 1. So I end up with 1 on x times 1, which is just 1 on x. So we can see that if I differentiate the natural log of x, I just get 1 over x. And this is going to be a really important formula when we come to apply these derivatives to other sorts of questions. Let's take a look at another example, but this time our y is going to be equal to the natural log of u, where u is actually a function of x itself. Okay, so for example, if y was equal to the natural log of 2x squared, then in this case, u would be a function of x, g of x, which is equal to 2x squared in this case. So how do we go about differentiating something like this? So we're actually trying to differentiate now y equals the natural log of some function of x. And we would do this by using the chain rule. So remember the chain rule says that dy dx in this case would be equal to dy du times du dx, okay? And in this case, it's our g of x that is equal to our u, okay? So this is equal to the natural log of u. So we can use u and g of x interchangeably. Now, what is dy du? Well, if y is equal to the natural log of u, then if I differentiate that with respect to u, just like we did previously, I just get 1 over u. Okay, so when we differentiated the natural log of x, we just got 1 on x. So if I differentiate the natural log of u, I'm just going to get 1 over u. And then I multiply this by the derivative of u with respect to x. But u, remember, u is equal to g of x. So the derivative of u with respect to x is just the derivative of g of x. And remember, we can say that our u here is just 1 over, so our u just being our g of x, multiplied by our derivative of u, so multiplied by the derivative. And we can just rewrite that as the derivative of g of x divided by g of x. So for example, in our case where we're looking at y being equal to the natural log of 2x squared, in that case, our g of x or our u would be 2x squared. So if I differentiate that guy, I just get 4x. So our answer to dy dx in this case would be my derivative of g, or my derivative of u, which is just 4x, divided by my g of x, which is just 2x squared. And I can simplify that down to just be 2 over x. So some of that proof stuff might have been a little bit complicated, and I'd recommend you go back and you watch that a couple of times. But to sum up, we have the following 2 rules, okay? If I differentiate the natural log of x, I just get 1 over x. And if I differentiate the natural log of some function of x, call it g of x in this case, that would be the derivative of that g of x divided by that function itself. Okay, now this might be written slightly differently. It might be written as an f of x or a h of x or a u or whatever it might be, but they all mean the same thing. And these are the 2 rules that we've kind of proven in this video.